Hello, I'm Natalie Rhea. Today I'll be discussing Lab 1, the charged tape experiment for Physics 2212. This presentation will include, first, an introduction of this lab, including a description of the experiment and a discussion of relevant fundamental physics principles. Next, observations, data collection, measurements, and interpretation of the results from the experiment. And lastly, a Glowscript model to visually depict the situation. First, the introduction. For the experimental setup, we first prepared two charged pieces of Scotch tape, referred to as U-tape, by quickly ripping two pieces of tape apart from one another. Next, we observed the interactions of the tape with each other and with neutral objects such as a notebook or our hands. Lastly, we used our observations and measurements to determine the excess charge on one charged piece of tape and calculated the net transfer of electrons. The first physics principle at play here is Coulomb's law, which states that the electric force between two charged particles is equal to Coulomb's constant times the charges of the two molecules, divided by the square of the separation distance between the two molecules. Another important concept is Newton's three laws of motion, that objects in uniform motion will remain in that state unless acted upon by an unbalanced force, that force equals mass times acceleration, and that for every action there is an equal and opposite reaction. In order to carry out calculations later in this lab, we had to make a few assumptions. First, that the pieces of tape should be treated as point charges, with charge and mass of the pieces of tape concentrated at their center. Next, we needed to assume that both pieces of U-tape have the same charge. And lastly, we needed to ignore air resistance on a moving object. Now, on to the experiment. Once the pieces of tape were charged, we observed their interactions with objects to determine whether the tape was positively or negatively charged. We noticed that the tape was attracted to our hands, as seen in the photo, that the two pieces of tapes were repulsed from each other, and that the tapes were attracted to a neutrally charged notebook and a plastic pen that was run through hair to give it a negative charge. From these observations, we could conclude that the pieces of tape were both positively charged. Once the charge of the tapes was determined, we suspended one piece of tape, piece B, as shown in the diagram. Next, we held up a second piece of tape, piece A, up to piece B. When A is brought close enough to piece B floats upward in the direction away from like-charged piece A. We then measured the separation distance between the two pieces of tape when the charges were in equilibrium, at the distance right before tape B begins moving upward. Our average measurement over the course of two trials was 0.0275 meters. As for other measurements recorded, the length of the U-tape was 0.2 of a meter, and the mass of the piece of U-tape is approximately 2/10,000ths of a kilogram. With these measurements, we were able to calculate the force of gravity on the piece of tape using the equation force of gravity equals mass times gravitational constant. The result was negative 1.568 times 10 to the negative third newtons. Because tape B isn't moving, it is in static equilibrium, so the electric force on the tape is equal and opposite to that of the force of gravity. Next, I rearranged Coulomb's law to solve for the charge of the piece of tape. I then used this value to calculate the number of electrons on one piece of tape by dividing the charge of the tape by the magnitude of the charge of an electron. Then the number of atoms in one piece of tape was calculated by dividing the tape's area by the approximate area of one atom. Lastly, the ratio of electrons to atoms in the piece of tape was calculated by dividing the previously calculated number of electrons in a piece of tape by the number of atoms in the tape. This value was found to be 1.883 times 10 to the negative 7th. Discussion questions. What if electrons had positive charge and protons had negative charge? What would change about the observations you made with your tapes and other charged objects? If the mobile charges in an atom were positive and not negatively charged, our top tape would have become negatively charged when the tape was ripped off. Electrons are left behind on the bottom tape, which would make the bottom tape positively charged and the top tape negative in this hypothetical. Why is it important to handle the charged tapes as little as possible? What happens when the charged tapes come into contact with your hands or other objects? When the charged tapes touch your hand, or any neutral object, electrons begin moving to neutralize the net charge of the system, so the tapes will lose their charge if they are handled too much. Lastly, I will show my Glowscript model of the floating tape system. On the left is the Glowscript code that I wrote to create the model on the right. In the model, the purple dot represents tape B, The yellow arrow is its electric force due to tape A, the blue arrow is the force of gravity on the tape, and the white dot represents tape A. The important calculations from this experiment are printed in the text box below the system model.